So, we're in the homomorphisms chapter. We've looked at basic definition, of course, which we were familiar with from the isomorphisms. So this basic definition is you've got phi g to h, and the homomorphism property says phi of g1, g2 is the product of the individual images. Okay, but we're used to that from the isomorphism, studying isomorphism. So this is called the homomorphism property. We looked at various properties that homomorphisms have. In particular, in proposition 11.4, we noticed that they send subgroups to subgroups. Hi, Laura. It's all right. Just doing a kind of summary introduction. So the homomorphisms send subgroups to subgroups. So if you got a subgroup G, it gets mapped across as a set into a subset of H, but it is again a subgroup of H over here. And similarly, they pull subgroups back. So if you've got a subgroup of H, if you pull it back, so you look at everything in G that gets sent into that particular subgroup of H, this is by definition a subset of G, and it will be a subgroup of G. And moreover, if the subgroup we looked at of H was normal in H, then it gets pulled back to a normal subgroup of G. So there's quite a lot of interaction and good interaction between a homomorphism and what it does to subgroups, both forwards and back. Okay. So then we have this section 11.2, the isomorphism theorems. And last time we proved, where we got to was the proof of the first isomorphism. So to remind ourselves what that meant. Now these isomorphism theorems, there's three of them, and in the middle is this other result called the correspondence theorem. They're kind of fully investigating kind of everything that can happen with homomorphisms and normal subgroups. So the first isomorphism theorem, it has this nice diagram that goes along with it. So you've got psi is a homomorphism. So it's a mapping between the groups G to H. And this theorem is kind of in some ways describes the possibilities for psi. What kind of maps, what kind of groups can you have on the other side of these homomorphic maps? What kind of variety of things is there that you can do a homomorphism into? Well, this map will have a kernel of psi. The kernel of psi, we proved that kernels are normal subgroups, because kernels by definition are the pullback of the trivial subgroup here. The trivial subgroup, the subgroup just consisting of the identity, it pulls back, its set of pre-images is by definition the kernel. And the trivial subgroup is always normal. So by the property we just reminded ourselves of, its pullback, the kernel would be a normal subgroup. So you can form this factor group. So this is the setup for the first isomorphism theorem, and then the conclusion is that there exists a map here called eta, and eta goes from the factor group G mod the kernel psi, and it's an isomorphism. It's injective onto the image of G. So the image of G may or may not be all of H, depending on whether psi is surjective or not. But there exists this map which goes from this factor group isomorphically to the same subset of H that is the image of G under the map psi. Okay. So this answers that question, is kind of, what is this group over here that we're able to map G to homomorphically? Well, what it is exactly the factor group of G by the kernel of the original homomorphism. That is isomorphically what the nature of this subgroup of H over here that we were able to produce this homomorphism to. Okay. This map here was called phi. This is always the This is the natural map from a group G to one of its factor groups, just sending any element to that coset of this norm. Okay. So these factor groups are these simplified forms of G, and this brings the homomorphisms into that same picture. Okay. The only groups that you can do homomorphisms from G onto are groups which are simplified versions of G. Simplified versions of G through this construction we already know about, which is this factor group construction, which is groups of cosets of a certain normal subgroup. So that was the first isomorphism theorem, which said given this setup here, okay, we already know about this factor group, and the conclusion of the theorem was that there existed this map here, which was an isomorphism. Eta is bijective when you restrict it to not necessarily to that it's going to be surjective onto H, but eta is injective, and it will be surjective onto the image of this subset of H. Yeah, so that's an important point. Eta is not necessarily surjective onto all of H, rather it is surjective onto image of G under the original homomorphism sign. But it is an injective map. So it's a homomorphism when we restrict the codomain of eta to this set. Okay. So that's a summary of where we were. So we'll now go on to the next result, which is the second isomorphism theorem, theorem 11.12. Second isomorphism theorem. Okay, so there's more isomorphisms here. So we'll read the statement of it. So we've got H, a subgroup of G. H, a subgroup of G. N, a normal subgroup of G. So Jan was using this notation. H less than G means H is a subgroup. N is kind of triangle less than G. And N is a normal subgroup of G. Then, so the conclusion is the product. Okay, this is a product of subsets. H and N are at least subsets of G. So we understand what this means. This means the set of all products, something from H multiplied by something in N. Okay, so it's a set of products. It's certainly a subset of G, but the conclusion is it's a subgroup of G. So H mod N, or H times N is a subgroup of G. H intersection N, which is certainly a subset of H. It's a non-empty subset of H because they're both subgroups, so they at least intersect in the identity. Okay. This intersection is normal in H. N is normal in G, but this is saying something more, that this intersection is a normal subgroup of H. And lastly, if we take get this right. I'm going to end up doing it the other way around. If we take Hn and take its Hn is a subgroup of G. It certainly contains N, because one choice for the elements from here would be the identity element. So some of the products in here are the identity element times any element from N. So this product of subsets certainly contains N. Therefore, n will be normal in it. So this factor group will be a valid construction. And the other conclusion is that this is isomorphic to H factor group by this normal subgroup of H. So once we know that this intersection, H intersection, is normal in H, that means this will be a valid construction of that factor group. Okay. So with this setup, with a general subgroup H, a particular normal subgroup N, it means the intersection of the two will be normal in the subgroup H. So you're allowed to form this factor group. But which factor subgroup of that, it's saying that, well, the structure of this is going to mirror, it's going to be isomorphic to the structure of taking a certain factor group, well, not quite a factor group, but the whole of G, but you just have to take these elements here, these elements from the product of the subsets, H times N. So there's a number of things to prove here. We have to prove this is a subgroup, this is normal, and then find what's the correct map here. Show the map is a homomorphism, and show it's one-to-one and onto. And therefore, it's an isomorphism. Okay. So generally, proving two things are isomorphic most of the time comes down to constructing the map, showing that the map exists, which normally in these kind of cases we have to give the definition of the map, prove it's surjective, and prove it's injective, prove it's onto and onto. Okay, so how proof of this? So first of all, let's take the subgroup thing. So certainly the identity is an element of H times N, because the identity is in both. So the identity, we can write the identity as E times E. So it's an element of H times an element of N. Okay. So the identity is present in this subset. See, we're starting off that remember Hn, by definition, the set of all products like this, H times N, where H comes from H and little n comes from N. Okay, it's a product of subsets. So it is, at the very beginning, we know it's a subset of G. G is the enclosing group, it's closed. So this is certainly a subset of G. It contains the identity. We then have to worry about to prove that it's closed. Okay. So to prove it's closed, we would take two generic elements from it. So one would be H1N1. Another one would be H2N2. These both look like two any old elements from the product. Something from H times something from N, something from H times something from N. What we want to do is to prove that the product is in H times N. So you consider the product of them, H1N1, H2N2. Now, is this an element of H times N? That's the question we've got to ask ourselves. Is this something from H times something from N? It doesn't look like it at the moment, because it looks like a quadruple product, something H, something N, something H, something N. But we do know H is a subgroup, okay, it's pretty generic, but N is special. N is a normal subgroup. And something about the format of this shows us some kind of relationship to normality. Now, this isn't quite a conjugate of an element of N. Remember, conjugates of an element of N would be something times N times the inverse of the original set, Gn, G inverse. Because N is normal, we know that N is closed under that conjugation. But the trick here is I know if we take any little n from n, I can always conjugate it like that. And that will be an element of n as n is normal. And what I'd love to be able to do, so any choice of little n from the subgroup n, this will always again be an element of n. Okay. What I'd really like to be able to do is to substitute that in for this n1. Because then that would cancel my h1 . I would cancel that h1 from the front. And I'd just be left with an n. So I'm trying to get closer to something from h times something from n. No, but maybe that's not what I want to do. No, excuse me. I want to get rid of that. Sorry. The problem is caused. I'm trying to make this be in h times n. This bit is looking okay because I've got something from h on the left. Sorry, this is the way I need to do it. I've got something on h on the left. The problem is, and then I got something from n, but then there's a h appearing here, but I wanted all the h stuff to appear on the left and all the n stuff to appear on the right. So it's this troublesome h2. So, okay, that's true, but that really wasn't what I wanted. Really, if we take any n in n, then h2n, h2 inverse will always be an element of n. That's the one I want, okay. I would love to substitute this expression for that n1. Because then I'd have h2 inverse beside h2, and that would cancel that troublesome h2 there. I'd be left with a h1, h2 in the front. That's okay. I'm allowed to have an element from h on the left. And I'd be left with some n times another n here. But that's okay because I'm allowed to have an element from n there on the right. So I want to get all the stuff from h on the left and stuff from n on the right. So the only question is which n is the correct n to use. So we want to find the n such that h2 n h2 inverse is equal to this n1, so I can substitute for that n1. But of course, that implies that the correct n to use is h2 inverse n1 h2. Pre-multiply on the left by h2 inverse, post-multiply on the right by h2, that cancels those two and leaves their inverses either side of n1. Okay. Is that an n in n? Yeah. This is an element of n as n is normal. Okay. So there is an n that works. There is something in the subgroup n such that when I conjugate it by h2 like this, I get this element n1. So I can then rewrite, so my product of two elements, this is my product of two elements from the product of the subsets. Something from H, capital N, another thing from capital H, capital N. I can re-express this now as, I'm going to replace it, I'm going to replace the n1 by this. H2 and H2 inverse, and then I've got H2 N2. I know this n exists because it's this element of capital N. Okay. So that's equal to H1, H2. H2 inverse H2 cancels, and I'm left with N2. And then it's just the observation that this is definitely in Hn. That's something from H times something from N. H is a subgroup, so it's closed, so this product is in H. N is a subgroup, so it's closed, so that product is in N. So that's element of H times element of N. Okay, so therefore, Hn is closed. Has inverses? Question mark. Does it have the inverses of everything? So you take an element from it. What does the inverse of this element look like? Well, the inverse of that is N1 inverse, H1 inverse. Well, we do a similar trick with conjugation. I want this to be an element of Hn. But at the moment, it looks like an element of NH, because it's something from N times something from H. Okay? But I think or maybe we don't even need to mess around with conjugates. We can just appeal straight to the normality of N. This is certainly an element of N, this right coset, isn't it? It's something from N. N1 inverse is certainly in N, because N is a subgroup. So it's an element of that right coset, but N is normal. So right cosets are the same as left cosets. So that implies that N1 inverse, H1 inverse is certainly an element of the left coset corresponding to that element. Okay. And that coset is a subset of Hn. Okay. Element or subset. Remember, this is the set of all this is the set of all products, something from H times something from N. This is the set of all products, this particular thing from H times anything from N. Yeah. So this is exactly, 1 over the size of H's proportion of this. Yeah. Things in here are anything from H times anything from N. These things are the things where, well, it's always this choice of element from H, but times anything in N. So this is a subset of the elements in there. So what were we showing here? We were showing here that this subset of G contains the inverses of all its elements, okay? Because the inverse of this is this, product of the inverses in the opposite order, but it is again present in here. So yes, so Hn contains all inverses, contains all its inverses. Okay, so Hn is a subgroup of G. Okay. It won't be true without the normality of N. Okay, because if you don't know that one of the subgroups is normal, then you'll struggle to prove the closure condition up here. Because if you don't, because it was only using the normality of N that we were able to fiddle around with this using the conjugation trick and reorganize it as something from H times something from N. If the containing group is abelian, of course, if the containing group is abelian, then yeah, you're completely free to just shove all the H's to the left and all the N's to the right, so the H times N will be closed. But if it's not an abelian group, and you just had H and N were just two subgroups, and you didn't know about normality of one of them, then you wouldn't be able to get this closure condition out. And you probably wouldn't be able to get the inverses condition out either. Okay? So you require that the normality of one of them is required. Okay.
Inverse.
Would the well,
that last implication of it is any inverse from an element N. So all the inverses of all the N's, little N, M1s.
Yeah.
And all. they form a subset which is definitely in HN as well.
So the I needed to use normality here to know that this subset is the same as this subset. This is a certain right coset of n. And here I was making use of the fact, okay, so now I know this is in there, but because n is normal, this left coset is the same subset as that. So I did so we were using normality here. Without normality, what this looks like is something from n times something from h. And you're going to struggle without normality and without commutativity of the operation. How are you going to reorder that as something from h times something from n? That's the difficulty. So it's the normality that allows me to know that this product is. Now notice I'm not saying here that this product is equal to h1 inverse times n1, little n1 inverse. I'm not saying that. I'm saying this is an element, it's probably h1 inverse times something else from n, not times that element from n. If the underlying operation is commutative, then it will be that element. But in general, it's probably expected to be some other element of n. But all I need it to be is there's some other element of n, which this is equal to this. And then I know it's again present in that subset. Okay. So that's only the first bit. Then we got to show, now need to show the intersection of h with n is normal in h. Well, consider a left coset. So a left coset of this by something from h. So this is going to look like a h times an x. Sorry, a left coset, h times h intersecting. Let's put a pair of brackets around that just to emphasize that. So. Well, what can we say about that? Well, an element from this, consider hx, where x comes from this. So this is an element of the left coset. I'm going to try and prove it's contained in the same right coset. Well, for a start, x is in n. So hx is definitely an element of this left coset. But that implies that hx is also an element of the right coset. So i.e., so that implies hx is equal to a yh for some y from n. Now, what do we know about y? We also know, in fact, y equals hx, h inverse. Just pre-multiply both sides. And this is a triple product, all of whose elements are in h intersect n. So that means it's again in h intersect n. Remember x came from the intersection? Oh no, wait, not in h intersect n. not to look at the book. H follows n being normal in G. You choose the fact that n is normal in G. But I've used it here. H of x will also be in the right coset. These right cosets are equal to right cosets. So hx is equal to that right product. I'm trying to show hx.
Y is already in there.
Y is an n.
We're trying to show that y is in H.
Y is in H. Sorry, yeah, I was going a bit too much. We can see that Y is in H from this, because X is in H. X is in the intersection, so X is in H. So this is a triple product of elements from H. So Y is an element of H also. So that implies that Hx is an element of the right coset of H. H intersect n by H. So first of all, I'm using the normality of n. Hx is an element of H times n, okay, because x comes from n. X came from the intersection. So by normality of n in G, I know Hx also comes from this right coset. The particular element of n that gives rise to it is, I'll just call it y. It's probably some other element of n apart from this x. If you look at what element it actually is, just shove that h over the other side, this y is hx, h inverse.
X is in n, which is normal, so that proves that y also has to be H.
Well, I think we already know that y is in n. What I need to know is that it's also in H.
Where did those H's go?
Yeah, this the
Because we considered some general left coset of this subgroup in the group. We already know that this is a subgroup of H. That's because it's an intersection of subgroups. I'm trying to show it's normal. So we consider a general left coset. This is a typical element. And we finish up by saying that typical element is an element of the right coset. So that shows that the left coset is contained in the right coset. Okay. The final little bit we needed was that y was in H, and that's because we see it here as a triple product of elements from H, because x was in this intersection, so x can be considered as being in H as well.
Is that just rearranging the previous line on the left?
To get that line from this, yeah, you just bring the H over on the right by H inverse, multiply both sides by H inverse there. So y is in H also, i.e. y is in the intersection. So therefore, what we've shown there is that the left coset is contained in the right coset. And if you just run the argument in reverse, in fact, those are probably equivalences. Similarly, the right coset can be shown to be contained in the left coset. So therefore, they're equal. The left coset is equal to the right coset. Okay, and this was true. This was just a general H from H, little h from capital H. And so that implies that the intersection of these two is normal in H. Okay. So we're ticking off the bits of theorem. We've proved the product of the two things is a subgroup. The intersection of the two things is normal in the general subgroup H. Now we come to the isomorphism bit of the second isomorphism theorem. we know n is normal in G. H times n is just some subgroup of the elements of G. So n will also be normal in that. Okay. Remember, normal means that if any left coset would be equal to the same right, equal to the right coset generated by the same element. So that's going to be true of a restricted set of choices of representatives. Maybe not the whole of G, just this certain subgroup of G. So n will be normal in this. So this is a valid factor group construction. We've just shown that H intersect n is normal in H. So this is a valid factor group construction. And now we're going to show that essentially the two are the same. They're isomorphic groups. There'll be different elements because the elements of this are cosets of n, right, which is big, n biggish. These will be cosets of H intersection n, potentially smaller because it's an intersection of n. Okay, so this factor group is built out of smaller bits. You're factoring a smaller group by a smaller subgroup. Here you're factoring a larger group by a larger subgroup. But the two factor operations produce groups that are isomorphic to one another. Now to prove that, we've somehow got to find a map between the two. So the main question that pops into your mind now is, what is the map? Well, now you see there's H's and N's all over the place. So these are intimately connected. So we would hope that the map arises very naturally. There's not going to be some weird, complicated formula for the thing. Just hope it to be just a straightforward, there's really only one possible way to do it kind of thing. Okay, so let's try and do it. So for the isomorphism, we need a map. Now, I think it goes in the other direction to which I wrote it down. Yeah. Yeah. So we can define a map. We can easily define a map phi that goes from H to one side. So that group is the group on the left. The factor of H times n by n. What is this map? This map, well, if you take an element little h, which coset of n are you going to map it to? Now notice I'm not changing this. This isn't necessarily an isomorphism. The isomorphism we want is from here to here, right? But at the moment, I'm only mapping from H to this with a homomorphism. And we're going to get an isomorphism later, thanks to our first isomorphism theorem. So these things have to be cosets of n. So, the one possible answer, which coset of n do you associate to an element little h? And it must be a coset by an element from this, so it must be an element h times something from n that you use as the representative. H times e, yeah. So just essentially just that same h. So don't needlessly complicate it. Just keep it as dead simple as you can. So just to that coset. Okay. This is certainly a valid element here. Okay, so it's a coset of n by something from the product h times n. As you said, e is a valid choice for the second factor in the product. So this is really h times e. We'll just write it as, just keep it as h. So that's our map. So a few things about phi. This map is a homomorphism. Is that? I think that's clear, isn't it? Because what happens when you try and do phi to h1, h2? You mean the coset generated by that element. But these are elements from G. This is a normal subgroup of G. From Jan's lectures, you know that is just the product of that is the product of those two cosets. Okay, just from the regular factor group notions. As n is at least, n is a normal subgroup of G. These are elements of G. We got fine, the overall containing group. And that is exactly phi of H1 times phi of H2. So it is a homomorphism. It satisfies the homomorphism property. Then I think we just, yeah, we will apply the first homomorphism theorem. First isomorphism theorem. So for the first isomorphism theorem, unfortunately I've called this phi. Okay, the things get renamed, the things aren't in the same location. So this is your starting off homomorphism. So, okay, we called it psi there. Unfortunately, it's now called phi. So that's our map across the top. But think of it as going across the top of the triangle. So we got H coming across to this group by phi. One thing I will, we'll worry about that in a moment. So let's figure out what the kernel of it is. Kernel of phi equals what? Well, it's the inverse image of the identity element. Okay. By definition, it's the set of all little h from H such that, well, phi of H is the identity element over here. What that means is that coset is the identity element. The identity element is the normal, is the subgroup N itself. Yeah? Which H's have this property? Which little H's have this property? When is a coset of N equal to N itself? That only happens when the representative you're choosing is already in N. Yeah, when the representative you're choosing is already in N. So that is equal to the set of H's in H such that little h is in N. Okay? Because a coset of an element by another element, it's equal to the same subgroup itself. It doesn't shift the subgroup anywhere, only when the element is already in there. So these products are all elements of there. But what's that better known as?
H is an element of the intersection Hn.
Yeah, but it's the set of all those little h's. So it is just H intersect N. Yeah? It's everything in H that is also in N. H intersect. Yeah. So that's the kernel. So we can complete our triangle from the first isomorphism theorem. Down here we have H mod. That is just the usual natural homomorphism from a group to a factor group of itself, sending each element to the coset it generates. So we know that there exists this map, let's just call it eta. So there exists eta, an iso from here to, well, phi of H. So what is phi of H? Actually, phi of H is all of this group, Hn mod n. Because given any subgroup, given any take a general coset here. Take a general element of Hn mod n, i.e. this is some coset of n by a product H1N1. Now, by associativity, you can write that as this. Remember, this thing is a set of triple products, H1N1, something general from n. This is a set of triple products, exactly the same thing, H1N1, something general from n. But by associativity, the triple product is unambiguous. But for our noticing, for our emphasis, we instead place the brackets there. Now, what's inside that bracket? It's a coset of n by a little n1, which is something from n. See, I wrote here a generic element H1N1, a generic element of that group. So what is a coset of n by an element already in n? Well, that is n itself. Okay, if you coset a subgroup by a representative already in the subgroup, that doesn't shift the subgroup somewhere else to some other subset of the group. It keeps it'll permute the elements of n around because you're pre-multiplying everything on the left by some particular element of n, but it remains the same subset, remains the same subgroup, remains n. So basically, this typical element of this factor group can come from under 5 from H1, because this is 5H1. Okay, because our map, how do we define our map? We defined our map. We just sent H to the coset generated by that H. Okay, so we can generate any coset of this from H. So that means 5H, that justifies this. 5H is equal to that, all of that. And so this map eta, which is the isomorphism, is actually onto all of this. That goes to your question from before. It isn't in the general statement of the theorem, it isn't necessarily onto all of this, it's just onto the image of this. But this initial homomorphism is actually surjective. Okay. So from the first isomorphism theorem, we get the required result, that H mod H intersect n is isomorphic to Hn. So these things are nice, but there's loads of maps flying all over the place, loads of cosets. It is tricky. No individual part of it is that complicated, but it's just marshalling it all on the page is really the issue, and just addressing each of the claims made, just patiently and bit by bit, and always trying to look where you can make use of stuff you've already proved and so on. Okay. So it still leaves us with